Is our universe truly the entirety of existence, or could it be just a brief chapter in an endless cycle of creation and destruction? British physicist and Nobel laureate Roger Penrose has a compelling answer. He firmly believes that the cosmos undergoes a perpetual process of rebirth and renewal. But there's more. Penrose claims to have uncovered concrete evidence supporting his cyclical model. He points to the discovery of enigmatic Hawking points in the cosmic microwave background, which he suggests may mark the locations where supermassive black holes from a prior universe eventually evaporated. What is now considered fundamental knowledge in cosmology was, just a century ago, regarded as a rather exotic idea. In fact, up until the mid-20th century, most scientists believed the universe to be eternal and, above all, unchanging. While stars might be born and die, planets could collide, and civilizations might rise and fall, the prevailing assumption was that, on a grand scale and over immense spans of time, the universe's overall structure remained constant. However, astronomers eventually discovered something extraordinary. Distant galaxies appear to be moving away from Earth, and the speed of this galactic retreat increases with distance. After numerous detailed follow-up studies, experts finally uncovered the true cause of these mysterious galaxy movements. Surprisingly, it isn't the galaxies themselves moving through space. Instead, it is space itself that is constantly expanding. In essence, scientists discovered that the universe is expanding, shattering the old notion of a rigid, unchanging cosmos. However, it wasn't until the 1960s that they realized this expansion, when traced back in time, pointed to an extraordinary singularity, the universe's origin. This discovery revealed that the universe was born approximately 13.8 billion years ago in what we now call the Big Bang. Such a profound astronomical revelation hadn't been seen since the acceptance of the heliocentric model of the solar system. Yet, even this comparison falls short, as we now understand the Sun is not the center of the universe but merely the heart of our solar system. As with many groundbreaking discoveries, this realization brought with it a host of profound and challenging questions. If the universe truly originated from the Big Bang, what came before it? What was the nature of space before it started expanding, and how long did it remain in this primordial state? Adding to this mystery is the notion that everything with a beginning must also have an end. But what will the ultimate fate of the cosmos look like? Could it resemble Roger Penrose's idea of a cyclical, eternal universe? Despite these profound questions being as old as the Big Bang theory itself, we still lack definitive answers. Even among scientists, there is no consensus. Instead, the field of astronomical research remains sharply divided into two opposing camps on the matter. Stephen Hawking once compared the question of what existed before the Big Bang to asking what lies north of the North Pole. Both are inherently nonsensical. Since time itself began with the Big Bang, nothing could have existed prior to it. In contrast, Roger Penrose offers a different perspective. As a theoretical physicist, Penrose collaborated with Hawking in the 1960s, contributing to groundbreaking discoveries about singularities and black holes. Decades later, in 2020, Penrose was awarded the Nobel Prize in Physics, or at least half of it. He earned his share for demonstrating that the formation of black holes is a direct consequence of general relativity. The other half of the prize was shared by Reinhard Genzel and Andrea Ghez for their discovery of a supermassive black hole at the center of the Milky Way. Stepping away from the realm of Nobel Prize accolades and returning to the main topic, we find that the seasoned physicist initially tackled questions about the origin and destiny of the universe from a philosophical perspective. Penrose first had to define what qualifies as a universe versus what does not. His conclusions can be summarized as follows: the defining feature of a universe is motion. Motion, in turn, necessitates the presence of at least two material or energetic objects whose relative distance changes over time. In the absence of such objects, or with only one, the result is a conditional space that cannot be measured. In such a case, it's impossible to determine whether space is infinite or compressed into an ultrasmall volume, as in a singularity. In this framework, concepts like speed and time lose their significance. As Penrose explains, the universe, it is believed, may eventually revert to an extreme state from which it could explode into a new existence. According to Roger Penrose, in the far distant future, the last elementary particle will decay, and the relentless expansion of space will eradicate the final photon. In this framework, the universe will continue expanding until all matter disintegrates into light, creating a strange environment where time and space lose all meaning. This peculiar setting ultimately sets the stage for another Big Bang. To clarify, Penrose suggests that this isn't a unique, one-time astronomical event but rather part of a recurring cosmic cycle. As noted earlier, Penrose envisions the universe as having a cyclical nature, marked by destruction and renewal. If this endless cycle of cosmic rebirth is real, however, wouldn't there be evidence to support it? According to Penrose, there is, and we've already discovered it. Could Hawking points be remnants from a previous universe? Roger Penrose, along with Daniel and Christoph Meissner and Paweł Nurowski, has uncovered a fascinating signal within the cosmic microwave background, CMB, that may reveal the true nature of the universe. Data from both the Planck and WMAP satellites show numerous circular spots, each about the size of the full moon. But what do these spots have to do with a cyclic universe, and why were they overlooked for so long? The answer lies in the nature of the CMB, a faint glow left over from the early universe. It was formed approximately 380,000 years after the Big Bang, during the epoch known as recombination. The background radiation continues to permeate the entire universe today, and its detection was anticipated by the Standard Model, making it strong evidence for the Big Bang theory. However, Penrose now contends that finding the so-called Hawking points provides compelling support for the cycle theory. These points correspond to multiples of the average fluctuations in the cosmic microwave background, CMB, temperature. Both the Planck and WMAP data identified these anomalies in the same locations, but they were previously overlooked because it was believed that cosmological inflation would have wiped out such features. Experts describe a stage of extraordinarily rapid expansion of the universe that occurred immediately following the Big Bang as cosmological inflation. This event, though lasting only an incredibly brief period, mere fractions of a second, had a profound impact on the universe's growth. During this moment, the universe is believed to have expanded by a staggering factor of at least 10 to the power of 26. To illustrate just how dramatic this inflation was, the region that now encompasses the entire observable universe originally had a diameter much smaller than that of a single proton. In an instant, it surged outward to a diameter of about 10 centimeters. The concept of inflation is not exclusive to the standard Big Bang theory, it also appears in cyclic models of the universe. However, these models differ in a significant way. Instead of occurring right after the Big Bang, inflation is viewed as a result of the ever-increasing expansion of the universe in the distant future of a previous cosmic cycle. In simpler terms, inflation can be seen as the outcome of the accelerated expansion that characterizes the end of one eon, a phase of the universe, giving rise to the next. In the context of the cyclic model, the universe undergoes an infinite series of eons, where each eon begins with its own Big Bang. This cycle is marked by a continuous loop, with each new eon emerging from the exponentially expanding remnants of its predecessor. This framework suggests a universe without a singular beginning or end, where each phase seamlessly transitions into the next through these episodes of cosmic inflation. The transition from one eon to the next is intriguing because it is supported by both mathematical and physical principles. The conformal compression that characterizes the cold, low-density universe of the distant future mirrors the conformal expansion of the hot, dense state during the Big Bang that ushers in the next eon. However, there is one notable exception to this seamless progression. On theoretical grounds, supermassive black holes present a challenge as they don't transition as smoothly into the following eon. By the end of the current universe, these colossal black holes would have nearly devoured all the galaxy clusters around them. Eventually, they would succumb to complete evaporation through Hawking radiation, marking a significant departure from the continuity of cosmic evolution observed in other aspects of the transition between eons. Due to what is known as the conformal squeeze, all the energy emitted is transmitted to the next eon as a single Hawking point. During this process, the photons produced scatter in an expanding space, but they are only released when they eventually become part of the microwave background radiation of the next eon. This region would appear as a disk to us, roughly the size of the full moon. It seems that such an effect might actually be observable in the cosmic microwave background, CMB. In other words, the enigmatic spots could represent the locations where black holes from the previous universe left their Hawking points in the background radiation.